Okay, so in the previous video, I explained we can include more variables if available and if you think they are important. So we extend the simple regression model to a multiple regression model. Earlier, we had only one x, right? So beta 0 and beta 1x was the end of the equation, plus epsilon, of course. But now we have x1 and x2 at the same time. So if you need to include more than 2, then you may keep going like x3, x4, x5. Does not matter. But for simplicity, I'm going to consider only 2 variables, which is enough to understand the differences from the simpler case. So in this case, beta 1 is still the same. This is the effect of x1 on y. So when x1 increases, y increases by beta 1. But you have to remember this additional phrase. We have to interpret beta 1 as the effect of x1 on y given that x2 does not change. Sometimes this is very important. And it's the ceteris paribus assumption, the basic assumption in economics, and sometimes in many analysis, people ignore this part, so misunderstand or get confusion by ignoring this. But sometimes it's very important. And the OLS can be used in the same way, using the same idea to minimize the sum of squared errors, right? And the minimization is not that difficult in this case either. And the fitted value can be calculated in a natural way, right? Naturally will be calculated this way. Epsilon does not exist, and use beta 0, beta 1, beta 2 estimators. And residual analysis can be done in the same way. Like you may calculate the sum of squared errors, you may calculate the regression sum of squares, you may calculate total sum of squares, you can calculate r squared, and you can calculate whatever, like almost everything can be done in the same way. So of course, if you care more about algebra, there are differences, but just conceptually I'm just giving you the basic idea, intuition, how we obtained the results. Then basically there is no difference, right? Extension is pretty straightforward. And I used the real data to include another variable, age. So age is the second variable I included, and you see just there is no difference. The only difference is maybe here, degrees of freedom in regression sum of squares becomes 2 because there are 2 variables now, and otherwise the same, but there is another line, another result line here, given here. And then I will ask you this question. Think about a person who is 30 years old and who finished 16 years education. What is the predicted hourly wage, hourly salary for this guy? Use the predict this person's hourly wage. Okay, the answer is calculated this way. Beta 0, intercept is this. Beta 1, the slope of age is this, multiplied by 30. And beta 2 is the slope of education, which is this, multiplied by 16 years. Because we specified 30 and 16 for these 2 variables, so we plug in those values there, and then you get 10.341. So should be straightforward, right? There is nothing special. fitted value can be calculated in the same way. And now I will ask you this way. Remember, statistical significance is a very important concept in regression models. And here we have two variables, age and education. Between them, what are statistically significant at 5% significance level? You may use critical value approach, t-stat approach, p-value approach, no matter what. And you may use these coefficients and standard errors and all the information here. Let me give you the answer. The answer is, so statistically significant at 5% means the null hypothesis of zero slope should be rejected at 5%. P-value should be smaller than 5%, and you may look at this p-value. Education has p-value small, equal to 0, but age has p-value of 20%, more than 20%, which cannot reject the null hypothesis. So age is not rejected, which means it is not statistically significant. Only education is statistically significant. C is the answer. A is not statistically significant answer. That means you cannot distinguish this coefficient from 0. So even if you believe that age does not affect your hourly wage, you cannot reject that. That's fine. So age has no statistical meaning in explanation to explain the hourly wage. So it does not help. And also what you can tell here is, even if age has little effect on the hourly wage, the coefficient of education changes a little bit. Of course, the intercept changes too, but coefficient of the education also changes from 0.743 to 0.741. So when you include additional variables, even if the additional variable is irrelevant, the existing estimators will change a little bit. Or if the effect is significant, then can change more than that. Anyhow, the point is, it changes. You have to recalculate all the estimators again when you include a new variable. But the way of calculation is, the algebra is the same as what you did for one variable. But now you have to do the same thing for more than one variable, right? Also, you may compare the r squared. Now the r squared is 10.66, 10%, about 10%, but earlier we had 10.6%. There is no increase, almost no increase. So remember, the reason why we wanted to include more variables is because the explanation power is weak, but because the additional variable is insignificant. Therefore, including this insignificant variable does not help explanation power, right? And so they are all can be interpreted in the same way. So that's how we extend a single regression model to more than one explanatory variable. Okay, this is the end of the main part of this course. Wow, finally, this is the end. Now I have 3 more pages to mention a few other issues. First thing, think about, so this is a graph from The Economist. When was it? You can find this graph from here, 2016. It's a very interesting story. It says ice cream induces anti-brain freeze. So it is evidenced by PISA reading score. PISA is the test score, standardized test score for students and across countries. So reading scores on the horizontal axis, and vertical axis is ice cream consumption. So it's clear that the more ice cream consumed, the more reading score, the higher the reading score is. So it looks like higher ice cream consumption improves reading skills. That's evidenced by this strong regression model. It's not linear, as you can see. It's a little bit curved, so more advanced technique is used, but idea is the same. R square is like 49%, which is really good. So reading score, the difference in reading score, nearly half of the reading score is explained by ice cream consumption, right? It's amazing. Of course not. This is April Fool's Day special report. Of course, doesn't make any sense. Ice cream has, even if ice cream helps like a brain or like something, but it cannot be this clear, right? If ice cream had this drastic effect, then all the doctors would recommend ice cream to students. Of course, the main problem is it's not about causality. So I explained as if X caused Y, but it can be dangerous. So in our earlier example, like say education and wage, in that case, I explained as if education caused the wage, because that's natural, like economically or just it's your common sense. Higher education induces higher wage. So if you can accept that interpretation is okay. But now, does ice cream induces reading score? No. Then there is no causality. It's just a correlation. So I don't know why there is a relationship, but there is a relationship. But it doesn't mean one is causing the other. Causality is very different from correlation. And usually it can be explained by this way: economic development. Think about, for example, if you had GDP, if you have GDP per capita, for example, then the higher the GDP per capita the GDP per capita will have a very strong correlation with reading score. At the same time, GDP per capita will have a very strong correlation, positive correlation with ice cream consumption. So as a result, through the GDP per capita, it looks like reading score has a positive correlation with ice cream consumption. So the confounding variable is the GDP per capita, for example. This is a huge problem where many, not only students, but many researchers make mistakes, right? It may potentially, maybe intentionally, or maybe mistakenly. So people want to argue that they find some interesting causal relationship, but often it's not causal. There are a lot of interesting examples, these stupid examples like this, right? I don't remember right now what else. There is another interesting example is the global temperature and the number of pirates, right? So number of pirates has been decreasing, so number of pirates and global temperature from 15th century, right? And since then, number of pirates decreased a lot. At the same time, the global warming was a very severe problem. So temperature goes up, pirates goes down. It looks like the global warming is caused by the extinction of pirates. So we have to allow pirates again. Of course, doesn't make any sense. Anyhow. And finally, again, nonlinear relationship is another thing you have to worry about. So when like everything so far we assume everything is linear, but if the linearity assumption fails, the result can be misleading. So I have given you examples like this. For example, pollution and GDP. So GDP, when GDP increases, does pollution increase or decrease? It's unclear, but usually what's said here is when a country is developed first, then pollution increases because they have to build factories and like use many plants. So pollution increased, but after a certain point, the country takes care of their environment. So as even the GDP develops more, but the pollution goes down. Take care of the pollution. So that's called Kuznets curve. And if you think about this hump-shaped relationship, linear regression does not work in this case. Like any covariance or correlation coefficient does not work in a nonlinear relationship. So, okay, this is the end of the course. Thank you for watching this, and I enjoy teaching. And have a nice holidays and have a nice vacation. If you need any help, feel free to let me know, and have a nice winter. Bye bye.